Ladies and gentlemen, please welcome to the stage the founder of Black Hat, Jeff Moss.
Good morning, everyone. Sorry, my voice is a little shot. I pretty much talked all day yesterday. It was fantastic just seeing everybody, and I couldn't shut up. So now my voice is suffering. So no, I'm not a clone or anything. So I'd like to welcome you to the day 2, our final day of Black Hat Europe. What I'm going to do is just remind you of a couple things. Turn off your phone. If you're going to let iOS update, it's probably about 20 minutes. Tonight there's a lock note to complement the keynote. It'll be this evening at 5:15. And what we do is we'll have some experts on the stage and we'll discuss what we've learned. And you'll really get a chance to sort of see the thinking of 3 of our review board members and some speakers, and get a chance to ask them questions, but really get to learn what did they make of all this and where do they think we're going. And it's a really nice way to sort of end the conference and try to put a lot of things in context. So that's this evening, 5:15. So it's my pleasure to introduce our event sponsor, Cylance. And when I'm introducing somebody, I always try to ask them to tell me something interesting or a little different that's just not purely security oriented. And it was interesting. So Anton Gratian from Cylance, who I'm about to introduce, he came to security through geology. So like a lot of us, we just kind of found our way to security. And he started the first managed security service provider before I think it was really even called a MISP for email in the UK. And so sort of through IT, he found security, and then through security, he found and got a degree in artificial intelligence back when it was expert systems, mostly, which has now evolved. And from there, he moved on. And if you know what Cylance does, the AI component matches pretty well for their products, and into security. And I like this. He's a beekeeper, so he knows quite a bit about risk. There are some trade-offs in beekeeping. So as a senior director for Cylance, he has responsibility for the EMEA region, and it's my pleasure to welcome to the stage Anton. Thank you very much.
Well, thanks, Jeff. As with all good introductions, I hardly recognize myself from that, so that's always a good start. So I'm not going to talk to you about beekeeping. I'm not even going to talk to you about artificial intelligence today, although if you want to talk about that, I'm your man. What I want to talk about today is unprecedented. Unprecedented is the word of most association with cybersecurity these days, and it's normally followed by number of threats, or increasing number of ransomware attacks, or surprising shortage in cybersecurity skills. Unprecedented is also one of the favorite words that we find in predictions, which there are an unprecedented number of predictions for what's going to happen in cybersecurity next year. And it's normally around about this time of the year that people are asked to give those. And they're very popular. Although there's one of my favorite quotes from Daniel Kahneman, who's a Nobel laureate, actually in economics. And he says that people who are paid to make predictions normally do a worse job than dart-throwing monkeys, who at least would have covered all the options equally. And that's because of human bias and the way that our 2 ways of thinking, fast and slow, actually interact with each other. But the predictions are always popular with organizations, with governments, with public sector bodies. And that's because of risk, the amount of risk that people are facing these days. And risk is okay. You can do a lot of things with risk. You can accept risk. So yeah, I'm going to continue doing the risky thing because that's what I need to do. You can mitigate it. And a lot of what we're talking about today at Black Hat is about mitigating risk. You can transfer risk. And one part of that is sort of cybersecurity insurance, which is becoming very popular as well. But the worst sort of risk you can have is the risk you don't know you've got. And organizations are facing an unprecedented task to keep their employees, their data, their networks safe from this unprecedented risk landscape that they're facing at the moment. And so their question to us is, well, where do I spend my increasingly tight, unprecedentedly tight security budget to minimize the amount of risk? So where do I get the biggest bang for my buck? Simple, isn't it? Easy. And really, that's what Black Hat's all about. In the demonstrations, in the trainings, in the talks, in the exhibition downstairs, we can all come together and understand what this risk landscape looks like, understand those risks and how to mitigate them, and therefore how to combat them. And so finally, on this last day of Black Hat, you've got an unprecedented opportunity to come together, to learn, to share, and to understand. Thanks very much.
Okay, so now it's my pleasure to introduce our day 2 keynote, Joanna Rakowska. And if yesterday what you saw was a larger global view, political, maybe economic, of some of the competing forces, today what you'll hear is sort of a technical view of how do we operate in compromised environments? How do we trust things that we know are essentially almost untrustable or unverifiable? And Joanna's had a long history in trying to confuse us as to what's real and what's virtual. She was famous for releasing one of the first hardware virtualized systems, Blue Pill, if you remember it. And it caused quite a controversy in the security community because some people are saying it was undetectable and other people are saying it was detectable. But what it really did is it launched us into this new era of virtualized security, virtualized rootkits, hypervisor escapes, and it really brought us to what I would say is sort of the modern era. And because Joanna came from sort of an attacker, offensive, malware, virus, Linux, Windows, rootkit, kernel exploitation, she really understands the mindset of offense. And that's really important because with her, since 2010, she's most famously known for her work on the Cubes OS project, which is essentially an endpoint, system that really doesn't trust anything. And so how do you function without trusting things and get work done and survive attacks and know when you've been attacked, minimize your... And so I thought it was going to be very fascinating to see how does she approach these problems? Because we all know they're highly technical, but we also know if you can fix some of these problems, it solves a lot of our day-to-day drudgery. So I'm really looking forward to seeing her. This will be the first time we've had Joanna back speaking at Black Hat since about 2008, so almost 10 years. So it's pretty feels really good to welcome Joanna back to the stage. With that, I'd like to introduce Joanna Rakowska. Thank you.
Okay, thank you. So security through distrusting is the presentation. So let's start with some terminology, which is related to the adjective trusted. So when we say trusted, such as trusted third party or trusted computing base, lots of people have this connotation that this means nice and secure, and that we would like all the things to be trusted. However, really the adjective trusted in computer security means that this object, this piece of code, this piece of organization, whatever is trusted simply means that it is capable of destroying my whole security, integrity, whatever. So actually trusted, when I call something trusted, I usually mean something opposite of what most people feel. I mean something very negative. I don't want things to be trusted. When we think about operating systems, we want to minimize trusted computing base, for example, the kernel. or hypervisor or whatever. And then we have secure. Secure, I use adjective secure in terms of to mean something that is difficult to attack. It not necessarily needs to be good for the user, because, for example, rootkit or backdoor, malware, and botnet can also be secure. A secure botnet would be difficult to be hijacked by another attacker. Essentially, it means it doesn't contain security bugs. And then finally, we have trustworthy, which somehow is what we really want things to be. So trustworthy means it's secure and good to the user, whatever it really good means, because good might mean something different for corporate IT, something different for an activist, and yet something different for another group of users. So trustworthy is a really very context-specific adjective. Nevertheless, we want things to be trustworthy. So trust considered harmful, this is the theme of this presentation. And I would like to show you a few examples, a few scenarios where I believe we can, by using some more or less simple tricks or approaches, somehow minimize trust. And let's start with something very, very simple. We all have mobile phones, and they have cameras and microphones. And the problem with this is that microphones are really, really annoying for security people. Now, modern phones cannot really be turned off. They are always connected. So if somebody compromises your phone, they can turn on the microphone and compromise you in multiple ways. For example, the microphone could probably help in figuring out your screen locker password, or, of course, record conversations that you don't want to be recorded, etc. I think this is quite obvious. So what we do, so that's what we have. But if we could imagine having phones without microphones, just physically removed. Oh, that's not a very useful phone, of course. But then we can have a Bluetooth set. And then whenever we want to talk, we use the Bluetooth set to connect to the phone, and we can make a connection. Now, the point here is that these two devices come from different vendors, which makes it significantly more difficult for them to cooperate and to create a covered channel for sniffing and for turning on the microphone. Of course, this is still possible, unless you have physical switch on your Bluetooth set, which is what I recommend. But this simple example shows how we can slightly improve the situation. Of course, this comes with quite a big usability trade-off, because I have another phone another iPhone which I have without microphones. I just physically removed all the microphones and also the front camera. And using it, I admit it's a beta, because whenever somebody calls me, I need to look into my purse, looking for the Bluetooth headset, put it on, and meanwhile the person disconnects. I need to call back, and etc. Still, it kind of works in scenarios where I would like to make sure that microphones are not turned on around me. Of course, if I meet with somebody else who has a phone with microphones, that makes quite little sense, but still. Anyway, that's a very simple example. Let's look at something more interesting. So imagine this green rectangle here is a motherboard of your laptop. And this motherboard contains lots of elements, like lots of microcontrollers. For networking card, of course, the processor, the chipset, sometimes integrated with the processor, sometimes not, embedded controller and disk controller, lots of things. And most of these microcontrollers contain firmware. And firmware is kept on some kind of flash memory, which is persistent memory, which means there are lots of places on a typical motherboard to persist malware, to store secrets. So if we have malware that operates deep enough, for example, in system management mode, or perhaps in Intel management engine, such malware can steal lots of secrets, like your keys, like your crypto keys, and they can store these secrets in those persistent elements. So it's quite worrying that we have all this persistent memory on motherboards. And even more worrying is that we can do very little about it. There is no reliable way, no reliable technology to, for example, audit or wipe those or reset to factory state. So that's really worrying. Practically wise, there's usually some little chip on the motherboard, which is called SPA flash, but it's not important, which keeps most of the firmware, or usually all the firmware. Of course, another firmware I forgot to mention is, of course, the BIOS. The BIOS, which is also the SMM, as well as things like management engine. We had two good presentations yesterday about management engines. You probably should be aware how evil or problematic it could be. So, is there anything we can do about it? Of course, we could hope for all the vendors, because it's not just Intel that produces firmware here, it's also the other vendors, like the BIOS vendors. We could hope for all these people, all these organizations to write secure and trustworthy code that will never have any bug, that will never be mean to the user in some way. Because let's not forget, we can have buggy code, and we can also have backdoored code. So even if the vendors had perfect coding skills, so they never make a security mistake, still they might just have an incentive to inject a backdoor of some sort. So we could hope for a perfect world with firmware that has no bugs, so it's secure, and also has no backdoors, so it's also trustworthy. But I'm really skeptical about it. Again, if you saw yesterday's presentation about ME, how easy it could have been compromised through a classic buffer overflow, and that was Intel's code. Intel, which is supposed to know their stuff, know their craft. Let's just think what is in all these BIOSes that are written by other vendors. So another approach is that I proposed some time ago is to move away the state carrying elements from the motherboard to outside the motherboard. Let's imagine we have a trusted element, trusted stick, where we put the SPA flash. And then we have whatever is on the motherboard are only elements are elements that do not carry state. Excuse me. Essentially, this means there are no flash memory on the motherboard. And then we have a well-defined interface between these two here. Which means that we can reliably provision firmware on the trusted stick. Perhaps not through our laptop, but through some trusted machine that will be in the IT department office or some other office. Even more so, we can perhaps have a switch here that will make it read-only. All of a sudden, all the attacks that try to persist malware on your firmware will bounce back because they won't be able to write anything to the firmware. Once you reset the laptop, it will boot up from the known firmware that you provisioned on day one. Of course, we get a reliable way to verify what firmware is there. This opens up an avenue for binary transparency database. As well as if we trust this little hardware, which is significantly easier to make this little piece of hardware trustworthy than the whole motherboard. This is just, a small FPGA. We can reliably write hardware, so this is provisioning. We can easily wipe the whole laptop and give it to another user. We just switch the sticks or cards or whatever. It could be like a SIM card. So that's another example of what I call security through distrusting. This has not been implemented yet, unfortunately. The biggest trade-off here, as I see, is actually lack of incentive for the OEMs to do that. Because what is really needed to implement this is to put a few different wiring, to change the wiring on the motherboard and to build the socket for this trusted element. So this is really, really cosmetic change, assuming some OEM will decide to do that. So here the trade-off is, or the reason we don't have it is, as I see it, lack of incentive. Okay, let's move to another example. This is multi-signature. So multi-signature, multi-party signatures are recently quite popular in the Bitcoin community, where you can have a Bitcoin wallet that can require multiple signatures to make a transaction, outgoing transaction. What I wanted to just stress here in this presentation is that multi-signature wallets does not need to, or are useful not just in the scenarios where you have several people, like different physical human beings. They are also quite useful where we have just one person, but this one person has, say, 3 devices, maybe a laptop, maybe a phone, and maybe another laptop. Maybe one runs cubes, another runs tails, or something. Or maybe Windows and Mac. And then each of these laptops will have one of these keys, and this person will just trigger operation by signing transaction on a few different laptops. In fact, in our project CubesOS, we have a public Bitcoin fund where people can, send us Bitcoins, and we actually use these scenarios where we combine these two. We have a few owners of this, and each owner has also a few keys kept on different machines. Well, the obvious trade-off with this approach is that it's a usability pita to make a transaction, because you need to do it on 3 or 2 or however many you want. You chose to make a transaction. And that's quite problematic, as in principle this is unsolvable, because if you wanted to have one application that would do this for you, that would somehow negate the whole idea, right? Because suddenly this one application will become the single point of failure, which is which we want to use the scheme to avoid the situation. So speaking about multi-user or multi-party signatures, it's worth stressing that they apply not just to cryptocurrency wallets. Much more importantly, an application that is very, very attractive, in my opinion, is to use them to sign binaries. So when I say binary, I mean different things. It can be something like OS installation image. It can be applications. You download applications installer. Importantly, this could be updates. Updates for your operating system, updates for your web browser, or whatever other updates you might be using. And of course, firmware, especially updates for the firmware. So you can probably imagine that an attacker who might be able to modify, especially your updates, it's a great opportunity for any attacker. If I was to target some high-profile individual, I would most likely not look for some remotely exploitable bug, which is often not very reliable. I would rather want to look into how to compromise the update build and distribution process for whatever software this person might be using. Probably the software with the weakest security. So maybe if the target uses Microsoft Windows and maybe Microsoft Windows update building is difficult, maybe I would target a browser security updates or just updates, or maybe browser extension updates. So let's take a look how the binary or especially update build and distribution process looks like very quickly. We can usually have 3 parties involved. We have developers, we have the vendor, and we have the end user. Usually these might be one organization, but it's not that important. So developers create software and then push to the build server. The build server builds the binaries and then distributes to users. Hopefully developers also not just create, but also cryptographically sign the software. For some reason, most of the projects don't do that and still don't do that. But that's quite important. It's also very important that all software, all source code be signed, because otherwise, it's usually software projects are not built in a vacuum. They make use of other software projects, and if other software projects are unsigned, then we don't really know what we are building on. But this is the topic I don't want to go into in this presentation. What I rather want to focus on is this middle step. So we have the build server. The build server just got a source code to build, and well, some processes start. A build process starts, might take hours, might take minutes, and finally the binary pops out. And usually there is a crypto key on the build server that is used to sign the resulting binary or binaries. And later these binaries are offered to users through some secure channels, say HTTPS. Or these might not even be through secure channels because the binaries might be signed, so might even be unsecured channels. Still, the binaries are signed and they're offered to the user. And the user is, before that, maybe before we go to this step, let's in a normal situation, the user, actually not the user, but the software on the user computer will accept the update, will check the signature, and we'll install it. We'll run it and install it. Now, the problem is that if somebody compromised the build server, that's a perfect opportunity to put a backdoor there. It might be a backdoor for all users or just selective. And the problem for the user is that there's no way to verify it, because if I put a backdoor before it was signed on the build server, then the verify will succeed by definition. So what we really would like to have for software that accepts updates, which is any software, to be able to verify that the binary it got really matches the source code that can be audited and can be reasoned about, that this is trustworthy or secure and trustworthy. But that usually doesn't work. It doesn't work for multiple reasons. One reason is that it's, for example, for any software that is not open source, we don't have access to source code. But even if we had access to source code, which is for all the open source code, the problem is that repeating the build process is very difficult, it's very resource intensive, and it's naive to expect that end users or their computers will be repeating this process. We have build servers for a reason, right? So what we can do instead is to have multiple build servers run by multiple organizations. Each of them will take the same source code, will verify this signature here, created by trusted developers, and will build the binary and will sign it. Now, assuming they will build the same binaries, we'll end up with having just one binary with multiple signatures. And maybe this is in Europe, this is in the States, this is in Asia. So for users who might have concerns about maybe the state interfering with the build process integrity, this might provide some more assurance. Or for an open source project, this might be different people, some of them working for company X, another for company Y, and yet another one for company Z, which might have different interests and different incentives, hopefully. So by using this multi-signed binaries, we can actually suddenly make the backdoor injection for attackers significantly more difficult, because they would have to compromise each of these organizations. So why is it not used by all the software? Actually, problem is, as far as I know, none of the software, or nearly none of the software uses it. I think Tor might be an example, an exception. The problem is that for this scheme to work, the build process, so converting source code to binary, must be deterministic. And unfortunately, which might be surprising to some of you, if you take complex enough source code, essentially any source code these days, and you compile it and build binaries from it, it will almost always be different. On different machines, it will be different, because there will be timestamps. Timestamps will go into the resulting binaries and images. They will, of course, differ. There will be differences because of the different number of threads used for the build process, etc., etc. And there is a project which is reproducible build, which is an effort between multiple projects, multiple open source projects, to actually get to the point where we have deterministically or reproducibly buildable software. And I'm really looking forward to this. Another example, preventing data leaks. That's a typical example for nearly anybody. We have some software that we might entrust with our sensitive data. Perhaps it is some office software, so we use it to write documents or whatever. But the problem is that it might just, either because it's malicious or maybe it's a feature of it, whatever. It's a feature that we might just not be aware of. It might be submitting our data to the cloud, for example, which from our perspective might mean that it's actually leaking our data. So of course, we can study every software very carefully. We can think about, we can test it. We can see whether it is going to save our files to the cloud, or maybe whether it's insecure and anybody can exploit it and steal our data from this software. Or maybe we just run this software on a monolithic operating system like Windows or Linux or Mac, where we have some other application there, which might be buggy and somebody might have exploited it and compromised it, and this will be leaking our data again. So what I'm trying to say is that we never know in practice. And this is another thing that is not really very optimistic. So there are some solutions for this. For example, we can put VPN and we can route all the traffic through VPN, and then the VPN will only connect to some trusted network in some corporate trusted network, preventing application, even if it wants to connect somewhere else, from connecting to somewhere else. It will always be routed there. That's a classic scheme for VPN. But there's a problem here, because if this all runs in a monolithic operating system, like say Windows laptop, maybe we have another application that is compromised, and maybe this compromised application will just compromise the VPN and will just change the settings or disable it or whatever, and will effectively will negate this or disable this scheme. So a smarter thing we can do is to put VPN on another device or another VM, where even if this is malicious or got compromised, it cannot do anything with the VPN. Whatever traffic it generates, it will always go through this VPN. Perhaps a better example would be if instead of VPN, I wrote Tor here, and we have some products and projects that uses this very scheme to do transparent verification of any traffic through Tor network. This is quite reasonable because you can have a web browser here, so you want to do anonymous browsing through Tor, but if your web browser gets compromised, and browsers get compromised all the time, right? So even if it gets compromised and wants to leak your data to, I don't know, FBI or whatever, it will always go through Tor and will always be routed to through Tor, whatever the software wants or not, whether it behaves correctly or not, whether there is malware or not. Another approach is maybe for some more paranoid scenarios. Let's say we want to work on some very confidential document. I don't know, perhaps you are part of the Black Hat review board and you got this PowerPoint presentation for review, but of course it's sensitive, you don't want to leak it out. So maybe a solution is to just cut off all the networking. Obviously, this will work, preventing leaks, but this might not be very useful in case you wanted, for example, to install updates. Perhaps you need updates to your Office to be able to render the latest version of PPTX presentation. Who knows? So one solution for this is it's a solution that we have in CubesOS. You can have a template VM, which is where you have software. So you have Office installed there, and this template has open access to the internet, so it can go to Microsoft servers, install updates, and then you shut down the template and you create what we call app VM, which is essentially copy of the template with user data connected to it. And this machine has no access to network. It's enforced by CubeOS logic. So it has a benefit of getting all the latest updates we installed here, but it couldn't leak it anywhere because it has no networking. And template, on the other hand, which has ability to go to network and request updates, has no access to user data because user data are mounted only to this VM, not to the template VM. Because we can have 10 or 15 app VMs for different purposes based on the same template. So this is just your root file system, and this is root plus home directory. Another example is compartmentalization, which we already started touching on. This is classic compartmentalization. Work VM, personal VM. Work machine, personal machine. Red, green, whatever. I say this is not very useful. This is not very useful because why would you think that if you run for a few weeks any of these machines, and let's say these are based on some popular monolithic operating system, again, Windows, Mac, or Linux, what makes you think that any of these would not become compromised just as if you just had one? You would still be opening attachments on your work VM and your personal VM. You would still be browsing to different websites that might just be malicious. And so what's the difference really? So to make it more useful, we want to also make sure that some of the risky operations, such as opening untrusted PDFs or media files or whatever, will also be handled in disposable VMs or other VMs. Well, I said disposable VMs because this is the concept that we have in CubeOS, but the point is they would also need to be isolated. Then it makes somehow more sense. But even with this approach, there are still challenges to make it actually practically more secure. My favorite is inter-VM data transfers. So let's imagine that you are making a presentation, perhaps for a conference, or maybe not for a conference. Maybe you make a presentation for a confidential company project, and just to show in your office, whatever. So non-public presentation. So obviously you are making it in some work-related sensitive VM, a secure VM. But what if you wanted to put a funny JPEG or PNG, whatever, some funny image you downloaded from the internet? You saw I put some image that I took from Twitter with the box with multiple locks. I downloaded the image from the internet, and this was my work VM, work office VM. So the problem with this was that if the image was somehow malicious, and it could have been malicious in multiple ways. It might have had malformed PNG or JPEG or whatever headers or some other data structures that when parsed by, say, Microsoft PowerPoint here would trigger some bug and exploit PowerPoint in this VM, will get code execution and will just steal all my data. Maybe stealing the data would not be so easy because my work VM doesn't have network access, but still it might have do some damage. So to somehow approach this problem, It's another feature we have in CubesOS is that we can have a converter that will be running in another isolated VM. In case of Cubes, this is disposable VM, where the whole rendering of the complex media, say a PNG or JPEG or PDF will happen, and then a conversion to much simpler format like RGBA array, which is a very simple format. That's what you want to know, will take place. And then here in this trusted VM, we'll have very, very tiny code, very simple code, just to receive this very simple representation. And it's very easy to write such code. It's very easy for this code to realize whether this is really the simple representation that it expects. And if it's not, then just drop it. And if it is, then it's a simple representation with no space for bugs, and then recreate the PNG or JPEG or whatever. So another thing about compartmentalization is that application sandboxing or sandboxing to work, personal, whatever, isolating PDFs, attachments is just part of the story. Another part of the story is that there are maybe something that's not visible to the user, but also very important parts of the operating system that we need to take care of and isolate. These are like networking stacks, USB, Bluetooth stacks, and other elements. For example, there were some presentations even yesterday about compromising Bluetooth stacks. So if we can keep them isolated, we don't care that much. The attacker exploits bugs here and is confined in these boxes here. It's another thing we do in CubesOS. Finally, I want to stress that isolation is just also part of the story, because the real challenge is how to take all these isolated compartments and present them to the user as one common desktop. So the integration aspect is what usually is the biggest challenge in making products like CubesOS, because it's relatively easy to compartmentalize and to isolate, but then you introduce bugs when you integrate it back. And it's really silly when you introduce bugs at the integration stage, which negate everything you have done before on the isolation phase. Finally, maybe not finally, but almost, another example is the admins. So the problem with admins is that they can steal all our data. So let's say these are user applications or files, or maybe VMs or devices, whatever. In a traditional corporate scenario that we have today is that users can access and work on their data, but they can't modify policies. They usually should not be able to modify software or install software, and that's okay. Problem is that admins, on the other hand, can do everything, including looking at user data, modifying the user data, which isn't very good. So ideally, you would like to have symmetric situation where admins can modify policy, can install software, but have no access to user data. And that's another thing. That's actually not so easy to implement in practice. It is not so easy because, well, once you get ability to modify software, as in applications or your operating system configuration, it's very difficult to make it to prevent you from stealing data. Well, nevertheless, we have been building infrastructure for this. For this very property in the latest CubesOS 4. Finally, you can be very, very paranoid. You can be very paranoid and you can take all these distrusting approaches, but occasionally bad things might happen. Occasionally your computer might get compromised. For example, in Cube's OS, unfortunately, still, we need to trust the hypervisor. We happen to be using Zen hypervisor because it has some beneficial architectural features, like ability to sandbox drivers and devices and to have backends in untrusted VMs, which other hypervisors do not really offer that. And if they offer, they usually are very academic hypervisors, which do not support hardware that well, etc. But Zen is like 200,000 lines of C code, which is a lot and still quite complex. And occasionally, security bugs are found in Zen. So occasionally, your compartmentalization, for example, might get compromised. So the final example is to have backup plan. And the backup plan seems easy. We have compromised or we suspect, because very often we cannot really be sure that the system has been compromised. The more skilled attacker, the harder it would be. But let's say we have suspicion that the system has been compromised. Perhaps because we just read a bulletin, a Zen Cube security bulletin or Zen security bulletin or whatever other for your software, and you say, that looks exploitable, and I recently visited a computer security conference and been using Wi-Fi network and this whatever. So what you can do is you can make a backup, and then you think you get a new laptop, and then you restore to the new laptop. Of course, there is no reason this should work, because if your computer was compromised and you made a backup, and then you are restoring this backup on the new machine, it's almost certain that this new machine will get compromised. There are hundreds of ways how this could happen. Starting from the fact that whatever you restore, the files you restore might be just compromised, and once you open the PDF, for example, from the compromised machine, it will just reinfect the new machine. Two more technical things that could exploit backup parsing code, and just own the system at the moment it restores the backup in multiple ways. So that's not a good solution. But that's another thing we've been working on in Cubes, and we have introduced some months ago, which we call paranoid backup restore, which uses, again, heavy compartmentalization and security through distrusting approach, how to actually take the backup, the potentially compromised backup, unpack it, treating it as untrusted, and create some subset of VMs that we say, okay, these VMs have been restored from this potentially compromised backup. Use it on your own risk, but you can still use it, assuming this, for example, hypervisor in this new, this is updated hypervisor, so it doesn't have this bug that we suspect was used to compromise the machine before. You could still be using these without affecting the other VMs that you might have recreated or restored from earlier backup, whatever. So just a quick summary that we saw some examples, and they can roughly be put in categories such as division of duty, like this mics and stateless laptop, or multiple signatures, more or less classic compartmentalization, and finally having plan B. I've been signalizing the trade-offs with most of these scenarios, but just to summarize it, probably the biggest pain is whenever we have trade-off on usability. such as in the multi-signature schemes, which almost by definition requires usability sacrifice. There are other areas where we have which all these techniques can impact our systems, and these are mostly fall into either increased resources, increased hardware resources. For example, if you run multiple virtual machines to have isolation, you pay the price of increased memory or CPU. Sometimes disk, but not necessarily. You can optimize it. But also, and perhaps even more importantly, you pay the price of increased resources on the development process. For example, whenever we need to add a new feature to CubesOS, such as support for remote management, it's not so straight. It's not so simple as in like most other systems. For example, the humankind has solved the problem of remote administration of endpoints, of course, but we could not just use it because that obviously somehow breaks the whole untrust everything model that we use in CubesOS. So it's been a slow process for us to create the infrastructure for accepting management and introducing it so it can be confined only to VMs that the user or admin wants to be affected by a specific management VM. So that's all from me. Thank you very much.